Good afternoon, everyone. We wait just a few minutes to leave the time to everyone to connect. Okay, we can start. Good afternoon, everyone, and welcome to the first Melodizer Webinar from Seawater to Freshwater, Innovative Path to Sustainable Desalination. My name is Cristina Schiavi from Tinexta Innovation Hub, and I'm glad to open this session on behalf of the consortium. Today's webinar marks an important milestone for Melodizer project. As many of you might know, the project is committed to advancing membrane distillation technologies to improve water use, reduce industrial water consumption, and contribute to sustainable desalination solutions. These goals are becoming increasingly relevant as water scarcity continues to impact communities, industries, and ecosystems worldwide. Our aim today is to offer a clear, accessible overview of the most promising direction in desalination, covering the current landscape, emerging innovations, and practical implementations. We are joined by 4 outstanding speakers from leading research institutions. Each will bring a different dimensions to the conversation. So let's have a look at today's program. We have Alberto Tiraferri who will start by presenting where global desalination stands today, status, challenges and opportunities. Alberto Tiraferri is from Politecnico di Torino. Then we have Matteo Fasano who will introduce membrane distillation, highlighting why it represents a promising path for energy efficient freshwater production. Then we have Alba Ruiz from PSA CMAT, will show how innovative prototypes are being implemented and tested in real conditions. And Mirko Frappa from CNR will conclude with insights into new generation materials and membranes that can further drive performance and sustainability. After the 4 talks, we will open the floor for a Q&A session. So I invite all participants to submit questions throughout the event, writing in the chat. Thank you for joining us today, and let's begin.
So it's my turn. I will share my screen with the presentation. Which you should all see now.
Yes, we can see it.
Okay. All right, let me start my stopwatch. So my role here today is to introduce desalination and tell you where we stand and the state of the art globally. And I will try to do that in 15 minutes, which is actually not a easy task. So why desalination? Salt water is a sort of non-conventional source water that we are kind of forced to tap in the future due to water scarcity and the fact that we cannot solely rely on conventional water sources. If we think about seawater represents the vast majority of the actual water on Earth. Fresh water represents less than 4% of the global water sources that we have on Earth. This is the current situation, and due to climate change and other factors, this ratio is actually destined to increase even more. So the proportion of salt water to fresh water will increase in the future. And actually, most of the population in the world, not most of the population, but almost half of the population in the world lives 100 kilometers from the coast, which makes seawater desalination a smart solution for water supply. But also we are talking, when we talk about desalination, we're also talking about inland desalination because we have plenty of brackish water or salty water also within the aquifers inland away from the coasts. Now, why is desalination difficult and why is it not already implemented at large scale? Because when we try to separate things, this is always a time and energy consuming task. Let's think about when we have a mixture of candies like we see here, it's very easy to mix them, but in order to separate the different colors, it takes time and energy. And desalination is even more difficult. It's more akin to when we have paints of different colors, for example, blue and yellow, and we mix them together to make green. And then if I ask you from the green to separate again the blue and the yellow, you understand this is a very, very difficult task. And this is akin to desalination that tries to separate water molecules from salt molecules. Despite of that, desalination capacity in the world is increasing fast. This is a graph showing the capacity for desalination in million cubic meters per day across the years from 1990 to 2020, and you see how it's increasing. The blue represents thermal desalination. I will briefly mention this later. The red represents membrane-based desalination, and as you can see from the graph, it's especially membrane-based desalination that's increasing in terms of capacity. There are actually more than 21,000 operational desalination plants in the world, treating both seawater and brackish water, as well as industrial wastewater that contains also, in many cases, salt. In terms of regions, by far, the dominant region in which desalination is being used today is the Middle East, which represents almost 40% of the entire market of desalination. So we're talking about Saudi Arabia, Israel, Iraq, Iran, Oman, Yemen, Egypt, above all. But also there is an emerging region, which is South Asia and Southeast Asia, together with the Australian continent. This is the fastest growing region. When we talk about numbers in terms of market size, these numbers here that you see in this slide are current numbers. Here we are 2025. So as also mentioned in the previous slide, we're about 20 billion US dollars today in terms of market size. But the projection is that there will be an increase, which is not a linear increase, it's more like an exponential increase in market size. And the market size is expected to reach 30 billion US dollars in 2030. Now, if you look at the different regions here, you realize that there is not a lot of growth projected for North America or Europe. There is a little bit of growth projected for Asia Pacific, that most of the market growth is projected again for the Middle East region, which is already the dominant region. It will become even more dominant in terms of desalination market size. In terms of the consolidation, the level of consolidation of this market today, we're basically somewhere in between a fragmented and a consolidated market. This is where we stand today, where this is fragmented market, this is consolidated, this is the market for desalination. And there are about 15 leading players in terms of companies that install medium and large scale desalination plants in the world, and they are listed here on the right-hand side. Now let's just focus a little bit on seawater desalination, which is not the only desalination. We can desalinate all sorts of salt water, as I mentioned, brackish water, industrial wastewater, but seawater desalination is, let's say, the most common type of desalination that we have today. So we have two state-of-the-art technologies that are implemented today. They are based on two different processes. One is distillation, which we all know about. We heat up water and salt, water evaporates, and then we condense it and we recover fresh water. The other process is called reverse osmosis. Here we use a membrane to separate the salt water from the fresh water, and we push salt water across the membrane, which only lets water pass, retaining all the salts here on this side, and so we can create fresh water that we recover on the right-hand side of this schematic. Now, the one important thing to say is that when we do seawater desalination and we start from a certain volume of feed, we cannot recover 100% of fresh water from that feed. We can only recover about 50%. And so the remaining 50% becomes a concentrated solution that we call brine. And let's remember about this concentrated brine in the next few slides, because I will say something about this. What's the energy consumption of desalination? Again, to separate water and salt, it takes energy. So if we look on the right-hand side, here is the energy costs of seawater desalination when we use distillation here, the orange bar. We go between 15 and 30 kilowatt hour per cubic meters of product water. For reverse osmosis, this is more energetically efficient, and we use between 3 and 8 approximately kilowatt hour per cubic meters, depending on the size of the plant and on the efficiency of the plant. This is still much larger than taking other sources of water to make fresh water, for example, surface water, groundwater, or starting from non-saline or low salinity wastewater. And the problem is that there is not much we can gain in terms of energy efficiency, because as you can see from the left-hand side here, there is a horizontal line here. This is the thermodynamics limit, so we cannot go below that. This is the minimum energy that it takes to achieve seawater desalination. And in 2008, this was the actual energy used in reverse osmosis plants. So we are already very, very close to the thermodynamics limit, and we cannot really do much better than that. So it's intrinsically energy intensive to do desalination compared to the treatment of other types of water sources. Let's put these numbers in perspectives. For those of you who are not familiar with energy numbers, an efficient refrigerator uses 1 to 2 kilowatt hour per day, which if we take 3 to 5 kilowatt hour per cubic meters, those are the best numbers for reverse osmosis seawater desalination today. This means that with this energy, we could produce between 250 and 500 liters of desalinated water. That's the same price of just keeping the refrigerator on every day. One warm cycle of washing machine is the equivalent of producing 75 liters of desalinated seawater. One cycle with drying of dishwasher, 350 liters of desalinated seawater, and just driving 6 to 8 kilometers with an electric car is the equivalent of producing 250 liters of desalinated seawater. So I made a calculation. If all water in Italy, for example, were produced by seawater desalination, it would require about 65 million kilowatt hour per day, and this would represent about 8% of the national energy demand. It's up to you to decide whether or not this is a huge number or a small number, and if energy and water are related very much. We need water to survive, but we need to spend energy, and it's a political calculation whether we want to go this way or other ways to provide fresh water to a population. In terms of cost, there are three items that make up the cost of desalination. One is the so-called delivery risk, which basically is the capital cost. One is the cost of capital, because we need to invest a lot of money to build plants, and so we cannot just pay the entire plant from the beginning. We need to loan money, and so we need to pay some interests. And then there are operating costs, which is mostly energy, but also other types of operating costs. And this is the cost of seawater desalination today, the best numbers. The two columns are for distillation, and the third column is for seawater reverse osmosis desalination. As you see, the price of water is about $0.76 per cubic meters. Actually, the best numbers I've seen recently are between $0.4 and $0.5 per cubic meters. Now, I recently participated at a desalination conference, and I actually talked to a person who we can define a market intelligence person, so someone who follows the market closely of desalination. So he's not a scientist, he's not an engineer, he is more economical scientist. And he mentions 5 threats for desalination today. So 5 issues that basically oppose desalination in the current global market. The first one is a stigma on brine management. Remember the brine, the concentrated solution that we produce when we do desalination. We need to do something with this. Right now, this is put back into the sea. And there is a bit of stigma on this. However, from a technical point of view, this is a very effective way to manage this brine, minimizing all environmental impacts. So all the other things that we do with brine that cost money may actually go against the market of desalination, because there is no actually need to do other things to the brine. We can just put it back into the sea, and we have shown from an engineering point of view that there is very little environmental impacts compared to the benefits that we have with this water supply. The second point, the second issues that he mentioned is the type of contracts. This is very important. It has nothing to do with technical stuff, but the way in which we build plants and we engage these consulting companies and these construction companies is very important to bring the price down. The third issue is that we are focusing very much on big plants. And when we talk about big plants, there are very few number of companies who are able to bid on these plants and construct these plants, which means that the market actually is dominated by only 2 companies in the world right now, really. And when there is no competition, there is no innovation. So this is not a good thing for the market and for the technology. There is a problem with perception and politics. Sometimes desalination is seen as a fixed solution to a temporary problem. Actually, water scarcity is not a temporary problem. So this is a fixed solution to a fixed problem. And finally, there is a problem with funding and where the funding goes. Sometimes going for technologies that will not succeed. And so it's seen from the point of view of investors as a waste and as a threat to desalination. Now, very quickly, in 1 minute, let me talk a little bit about brine desalination and valorization, especially when it comes to recovery of materials from the concentrated solution. So again, when we talk about seawater desalination, this is not necessarily the case. We should not probably do that from a techno-economic point of view, but for other types of streams, or when we want to achieve for some reason minimal liquid discharge, what we can do is first of all recover resources from this brine. And this graph here shows what the European Union thinks about recovery of minerals. And in the graph there is the risk of supply of different minerals and economic importance. So if we sit over here, these are very important minerals, for example, magnesium, that we can recover from concentrated brines. And there are all sorts of emerging technologies that we are developing as engineers and scientists and researchers to do that, and also to deal with very, very high salinity solutions. And one of them, I will not go through all of this, but one of them is membrane distillation, which can treat hypersaline solutions. And we will talk about this in the next presentations. The last minute, I will just mention that most of these new emerging technologies trade efficiency for sustainability. Today, the techniques that we use for desalination, distillation, and reverse osmosis, they're based on the use of mechanical energy and high temperature thermal energy. So basically mostly on electricity, so what comes from the grids and from burning fossil fuels. However, future technologies will rely more and more on low temperature thermal energy, which means that we can use low enthalpy sources, or if you wish, we can call them renewable sources like geothermal energy, solar energy. So in conclusions, desalination will be playing an increasing role in water supply. The golden standard today remains reverse osmosis, and above this salinity of about 50 grams per liter, we can only use distillation and evaporation processes. Together with seawater, also brackish water, desalination is growing, together with brine desalination and valorization. There are emerging technologies that trade productivity with sustainability, but many challenges need to be faced for their implementation. We will hear about some of these today. And beyond technological innovation, other issues are critical, like contracts, legislation, public perception, and financing. Thank you for your attention.
Thank you, Alberto. So now we give the floor to Matteo Fasano from Politecnico di Torino, that will introduce membrane distillation, highlighting why it represents a promising path for energy-efficient freshwater production.
Hello.
Hello.
Good afternoon to everyone. I share my screen. Hope you can see it.
Yes, we can.
Okay, so we'll continue in this presentation the discussion that was introduced by Alberto. So here in particular, we are going to focus on emerging, even if it has been around for at least the last 40 years, desalination technology that is trying to find the right segment of this huge market of desalination and of industrial saltwater treatment. So, as was mentioned earlier, the state-of-the-art technology, at least at a larger scale, are mainly reverse osmosis. The vast majority for desalination is reverse osmosis. That is requires high exergy sources of energy, so it is electrically driven. It has also some complexity in the plants since it requires high pressure. And so requires very large plants to be implemented, but at the same time has the best thermodynamic efficiency. Then there are some residual percentage of the market of desalination that rely on this multi-phase distillation, multi-stage flash, so some other thermal technologies that are still requiring large plants and high temperature. So here on the right hand side, you can see a table that actually compare for different criteria the advantage of one or the other technologies. And membrane distillation, the technology that we're going to talk in this presentation, has some points of competitiveness respect to the standard industrialized other two technologies, mainly when we talk about high salinity feed waters or brines, when we want to deal with the small scales, so not large plants, not plants that should provide water at the regional or city scale, but smaller ones. And also when we have energy sources with low exergy, so when we have typically heat at temperature that are below 80 degrees C, so waste heat or direct solar heat. And also it has the advantage of being able to treat high salinity and brines, which for the other technologies is quite complex. But of course, there are some drawbacks that we are going to explore. So membrane distillation should be seen, of course, as a complementary technology respect to the two predominant ones, which are reverse osmosis and the other thermal technologies, in some specific case studies and some specific application that also we are trying to address and explore with the Melodizer project. So a very quick and non-technical introduction about the mechanism that drives this distillation, this desalination technology. Basically, you need a hot salty feed, which is your feed water to be treated. And then you need some cold distillate, or at least a cold surface where you can have some condensation. This is a schematic, so here you can see this is a particular layout that is called direct contact distillation. We'll see later. Basically, you have this hot salt water to be treated, then you have a cold distillate on the other side. The two are separated from each other by a hydrophobic membrane, which is a membrane that actually allows you to block the liquid water, so the liquid water cannot pass through, while allowing only the vapor phase to pass. Why I'm talking about water vapor? Because given this temperature difference across the membrane, this temperature gradient that counterbalance the salinity gradient across the membrane, and in particular the thermodynamic quantity that is important here is the so-called activity, which is inversely proportional to the salinity. So this temperature gradient allows the water vapor to naturally tend to go from the hot side, salty side, to the cold side, which has low salinity. And this is manifested into a vapor pressure gradient that manifests from the top to the bottom, which is the actual driving force of the membrane distillation. This is what pushes water through the membrane, water vapor through the membrane. On the other side, the selective nature of the membrane keeps the liquid phase and all the salts and non-volatile contaminants on the feed side with a rejection that is approximate 100%. There are several engineering implementation of this principle with some slight changes. What I was showing earlier is the so-called direct contact membrane distillation, where you basically have two streams, the hot stream on one side and the cold stream on the other, and the membrane is just between the two. And it has some advantages, for example, the simple design, but also some drawbacks, since you may have lower efficiency, higher heat losses. That's why many applications now are focused on air gap membrane distillation, where the feed side is still the same, but on the permeate side, you, instead of having a cold stream directly, you have a very small air gap with a few millimeters or even lower. And then you have a cold plate, which is cooled down by a cold stream. And the advantage now is that the cold stream can be not necessarily distilled water, but can be anything. It can be also some processed water or seawater itself. And then you collect the condensate vapor that creates in the air gap. The only drawback of this is the relative complexity of the configuration. And then you also have other more, let's say, lab level, like vacuum MD, sweeping gas MD, other solution, and further with respect to this main one. So if we want to provide some KPIs, key performance indicators of the membrane distillation, first of all, the most important component is the membrane. Okay, so the properties of the membrane that provides, according to the thickness, porosity, and all the other properties, provide you some membrane performance. And at the end, membrane performance plus the engineering fluid dynamics of the modules and of the plant provide you the system performance of the membrane distillation technology. And these key performance indicators are basically the permeate flux, so the permeate, the distilled water that is produced in liters each hour of operation, each square meter of the membrane. The surge rejection, so how much salt is rejected from the feed to the produced water. And then the thermal efficiency, so given 100 kilowatt hours of thermal energy available, how much cubic meter of distilled water you produce, which sometimes is also called specific energy consumption. To play with this, you can clearly work with the type of membrane, type of module, but then there are some operating parameters you can play with, like the feed temperature, permeate temperature, the temperature different across the membrane, the mass flow rates, the geometrical, mechanical design of the modules, and the salinity you can have. And this is quite complex, even if it has been studied for many years, but it is a quite complex problem, very case dependent, that require models, especially fluid dynamics models, and that help you to find the best trade-off that you may have in the operation. So for example, just to name a few, higher temperature gradient across the module means higher flux, but also potentially higher heat losses, the risk of increased risk of scaling, and also typically higher exergy you should pay for your heat source. Or higher flow rates is typically nice to have better mixing, so reduce polarization, but require higher pumping cost, and for some configuration maybe even detrimental. So just to mention that there are many parameters to play with, and the optimization is required case by case. And we'll see an example at the end of this presentation. Membranes that are typically adopted for this technology, which is the core part of the technology, are polymeric, are hydrophobic, PTFE, PVDF, PP. These are the standard membranes produced already on the industrial scale. They have pore size in this range, so in a few tens of microns. They should have high porosity, not too high to avoid wetting, membrane wetting, and so basically to increase the liquid entry pressure. And they should be as thin as possible to reduce the mass transfer, to increase the mass transfer. These membranes then are packed into modules in different configuration, for example, in a plate and frame configuration, with hollow fibers configuration, so in a tubular mode like a shell and tube heat exchanger, or as a spiral wound module to have a compact system. And finally, there is an additional component that is typically included in the modules, especially in the plate and frame ones, which are the spacers, which are some grids, some porous medium, let's say, that enhance mixing and so reduce polarization and losses in the module. So limits of membrane distillation from a fluid dynamics point of view are basically polarization, wetting, and fouling. You have these two mechanisms. One is the temperature polarization, the other is concentration polarization, which is basically the lower value of the temperature gradient and of the concentration gradient that you obtain at the interface of the membrane with respect to the bulk ones. And this is basically due to the boundary layer that creates in correspondence of the membrane. This is detrimental because reduces the driving force to produce the water vapor, and can be reduced by optimizing the fluid dynamics within the modules and also the operating conditions. Then there are other problems that are wetting. If for some reasons you exceed the maximum liquid entry pressure that can be sustained by the membrane, then the membrane gets wet, so liquid water enters the pores and compromise the rejection. And then scaling and fouling, so the accumulation, for example, of inorganic scaling, carbonates, for example, and or organic biological fouling that you may have. So that's why it's always very important to pre-treat the feed water with some preliminary treatment processes. But in general, membrane distillation is more tolerant respect to reverse osmosis, for example, to this type of issues. As was already mentioned by Alberto, nowadays membrane distillation is very attractive when you have to deal with high salinity brines, for example, as byproduct of reverse osmosis, mining, and food and beverage. When you want to obtain zero liquid discharge desalination, or if you want to develop small-scale plants, so some plants that are not very large, produce not a lot of water, and that might serve off-grid communities. There are still some obstacles. The main one is the energy efficiency. It's true that we use low exergy energy, so waste heat or heat at low temperature. But if you do the calculation, overall, the amount of energy that is needed is much higher respect to reverse osmosis. So if the cost is not an issue, of course, this is a problem. The cost of energy is not an issue, this is a problem. Still, membrane durability should be addressed, and also we are exploring a clever integration with renewable sources of energy. And this is one of the topics we address in Melodizer, where we basically investigate direct contact membrane distillation and also air gap membrane distillation with a twist, let's say, because on top of the bulk heating of the feed water provided by solar thermal panels, we also provide direct solar irradiation to the top side of the module in order to provide a distributed source of heat to the feed water. This has interesting benefits because you basically increase locally the temperature of the feed water just in the proximity of the membrane, so you reduce the temperature polarization that you can get in your module. And these are some results that we obtain, as you can see, going from 0 watt per square meter, so a classical module, to 1000 watt per square meter, which is the, let's say, direct solar irradiation. We can get a quite interesting enhancement of productivity. And in particular, we have investigated the many operating parameters and geometrical parameters of these flat modules. And we have identified the best operating parameters to get the optimal results of production for this given configuration. For example, here, the color is proportional to the enhanced productivity with respect to no solar irradiation. And so if you get very reddish colors, you can get very high enhancement. And as you can see, the best results are obtained when the module length is quite large, 50 centimeter, the temperature is quite low of the feed, 40 to 40 degrees C, and also the mass flow rate of the feed is very slow, something around 1 millimeter per second, which are very atypical operating condition respect to the standard membrane distillation, but highlights how different configuration of membrane distillation require different optimal conditions. And finally, this analysis was done numerically, and we are now building 2 demonstrators, one in Almeria, and the other is an emergency desalination kit that we are going to test in Eilat, that want to implement this hybrid bulk and direct heated air gap membrane distillation to provide some distilled water to off-grid communities, or in case of emergency where you can easily deploy a water production technology. So to conclude, membrane distillation is a thermally-driven desalination technique where the core element is a hydrophobic membrane. It is very interesting technology for high salinity feeds, both brines but also industrial wastewaters. And whenever you have low-grade or solar heat available, which is typically wasted, it's key element to optimize the performance, finding the best operating and geometrical conditions. And also we have demonstrated interesting new layout of this technology, like the hybrid bulk and direct solar heating. And with this, I thank you for the attention.
Thank you, Matteo. So now I'll give the floor to Alba Ruiz from PSA CIEMAT that will show how innovative prototypes are being implemented and tested in real conditions. Thank you, Alba.
Thank you very much, Cristina. I'm going to share my presentation.
Yes.
Okay, hello everybody. Today I'm going to talk about the sustainable implementation of membrane distillation system. That means that to couple the membrane distillation system to a heat source, we need a solar energy field because we need the solar energy as a heat source to be sustainable in the ND process. When we consider a solar membrane distillation system, we consider two loops of the system. One loop is composed of the solar field, the heat source loop, that is composed of the solar field and also the heat storage tank. The other loop is the desalination or the bright loop, that is the membrane distillation module. Both loops are connected through a heat exchanger. So we have three different elements in the membrane distillation system. One is the membrane distillation model, the other is the solar field, and the third one is also the thermal energy storage. Here we can see a view of the Plataforma Solar of Almería facilities, and we have two different solar fields that we use to couple with membrane distillation. Both of them are based on flat plate collector, and one of them is this and the other one is this. This second one is the solar field that is going to be coupled with the membrane distillation system that is going to develop under the Melodizer project. The first solar field is composed of flat plate collector, in particular of 4 different large aperture collectors connected in parallel that in total has a total surface area of 40 square meters. This means a nominal thermal power of 14 at a temperature of 90 degrees Celsius. Also, this solar field has a heat storage tank of 2.5 cubic meters of capacity. The other one is the solar field that is going to be coupled with the Melodizer prototype. It's composed of 3 different rows of 5 collectors, each one with a total surface area of 20 square meters. The nominal thermal power of this solar field is 7 at a temperature of 90 degrees Celsius. In this case, the heat storage tank has a lower capacity than the other one, with a total capacity of 1.5 cubic meters of water capacity. We consider an indirect connection between the solar field and the membrane distillation system, because we don't connect directly the solar field with the membrane distillation system. We connect through the heat exchanger, through the heat tank. This connection has a call that is the indirect heating of feed, and has several advantages respect to the direct connection of the solar field with the membrane distillation module. This indirect connection, the advantages of this connection is that when the solar radiation and the ambient temperature have variation along the day, we can dampen these perturbance, and we can consider a stable condition in the MD module for more time along the day. So the heat storage plays a very important role, apart to considering a stable state condition in the ND operation. Also, the heat storage tank can reduce the size of the solar field that is needed for the particular application of a ND system. Now, to see this final point, the reduction of the solar field when we use a specific heat storage tank, I'm going to explain A particular study carried out here at Plataforma Solar of Almería in the project Melodizer, that is the use of a particular material, ceramic material, that is inserted inside the heat tank in order to use as a heat storage instead of the water. The study was based on a model, and 3 different objectives was reached. One was to improve the total water production, the other was to reduce the total surface area of the solar thermal field, and the third one was to reduce the cost of water. The parameter considered in the model was different. One of them was the solar radiation and also the ambient temperature of Almería. Almería is the place where is the province where the Plataforma Solar of Almería is located, and was considered a total year of the radiation and ambient temperature of this province. The other parameters considered in this model was the flow rate in the solar field before to the heat storage tank, also the flow rate after the heat storage tank and before the heat exchanger, and finally the flow rate that is inserted in the ND module, and also the temperature that we want to reach in the hot side of the ND process. 3 different scenarios were considered. The first one was to model the real size of the solar field that is here at the Plataforma Solar of Almería facility, the real dimension of this solar field. The second one is consider this real solar field with the real size of this solar field, but considering that the heat tank is filled with the backup burn material instead of water. And the third scenario is to consider a reduction of the size of the solar thermal field, and also to consider the use of the backup burn material in the heat storage tank. The total water production is considered in the model are 2. One is 10 cubic meters per day and the other 100 cubic meters per day. And also the salinity is considered brine solution between 70 grams per liter and 200 grams per liter. So considering the objective of improving the total water production, if we compare the use of the real solar field with the real solar field with the backup bed material, we can see that the use of the backup bed material increase the productivity, the permit productivity in the ND plant in a 20%. Now, if we consider the same quantity of water that we want to produce and considering a reduction of the total surface area of the solar thermal field, if we compare, we can see that we can obtain the same quantity of water with a solar field with a lower size of the solar field using the backup bed material. And finally, if we compare the 3 scenarios, we can see that considering a solar field with a lower size and also including the backup bed material in the hot tank, in the storage tank, we can reduce the cost of the water up to the 50%. This is because we are increasing the water production with the same size of the solar field, but also we are reducing the solar field, the size of the solar field that is needed. So the cost of the solar field is lower. The CapEx costs are reduced with this configuration. And now the second part of the optimal coping between the solar field and the membrane distillation system is to apply a control system between both, ND and the solar field in order to operate the solar membrane distillation system in an optimal condition, increasing the permeate production, but also reducing the specific thermal energy consumption in the total operation. For that, it needed to implement different control system in order to optimize the process of the solar membrane distillation. Here, to develop the control system, is needed to develop different models for the different elements that compose the solar field. These are the flat plate collector, that here we can see the equation used for develop the models, and we can see that the simulated water temperature is practically the same of the real temperature. So this model can simulate perfectly the water temperature that's outlet in the flat plate collector. Also, here we can see the different equation used to modulate the storage system. And finally, here we can see the equation used for the heat exchanger. And again, we can see that the simulated temperature and the real temperature are very similar. So at the end, the development of the control with the objective of maximizing the distillate production and minimizing the specific thermal energy consumption was totally successful, because was reached an increasing of the distillate in a 7%, considering a system with control system and another without the control system applied, and also the specific thermal energy consumption was reduced 1%, comparing also the two coupling, the coupling with the control system and without this control system. So finally, I would like to thank the group that is working in the Melodizer project, with a special thanks to Lidia Roca and Alejandro Hueso, that are involved in the studies carried out, also presented in this talk. And that is all. Thank you very much.
Thank you very much, Alba. So now I would like to leave the floor to Mirko Frappa from CNR. He will conclude with insights into new generation materials and membranes that can further drive performance and sustainability.
Thank you, Christina. Can you hear me?
Yes.
Okay. So let's start with my presentation on new generation and green materials membranes. Membrane technology is well recognized by the European Commission as one of the best available technology today. It fits perfectly with the ideas of process intensification and the sustainable development goals. This because membranes can be considered in general as a green technology, thanks to their advantages such as easy to combine with the existing system. They keep low operating cost and low energy consumption, and they can be considered as safe. There are also allow us to scale up processes smoothly while offering high efficiency and good stability, always with a small environmental footprint. The concept of sustainable development is simple: meeting today's needs without harming the ability of future generations to meet theirs. In that industry, this often means rethinking long-established processes, improving production methods, reducing energy and resource consumption, and looking for new materials and chemicals that are safer for the environment. One of the main strategy to make membrane production more sustainable is applying the principle of green chemistry. The number next to the box indicated the priority for making membrane fabrication more green. In practice, this means choosing safer materials, especially when preparing membranes, replacing traditional toxic solvent and polymers with greener alternatives, creating cleaner and simpler processes, and reducing the environmental border through the entire life cycle of the membrane. So this means we have to replace the traditional polymer and solvent with biopolymer and green solvent. For what concerns the biopolymer, we can see how the interest on these materials is growing in this last period, especially for the biopolymer such as PLA and PHA. And depending on the origins of these materials, we can classify the biopolymer in biomass, microorganism, and biotechnology. These materials should be renewable, biodegradable, compostable, carbon neutral, and safe for both humans and the environment. The market for biodegradable plastics is expanding quickly, showing that industries are increasing interest in greener materials for future membranes. Another crucial aspect concerns the solvent used to make membranes. A solvent is not green just because it's not toxic. We also need to think about how much energy it requires, whether it can be reused or recycled, and what its total environmental impact is. Some example of green solvent are Sirene, Polar Clean, ethyl lactate, propylene carbonate. However, replacing traditional solvent is still challenging because many of them are difficult to replace without affecting performance. In membrane fabrication, solvents play a central role. They determine how the membrane will look and how it will perform. They need to dissolve the polymer, interact properly with the water during the phase inversion step. Unfortunately, many of the conventional solvent usually, especially for PVDF membranes, polymers, sorry, are toxic and pose risk to human health, such as reproductive toxicity or respiratory issue. That's why finding a safer, greener substitute is one of the priority in making membranes manufacturing more sustainable. For this reason, I would to focus my presentation more on this aspect, on the green solvent, by talking of two case study. The first one is the Polar Clean, and that is a not toxic solvent with a high boiling point, and it has already been successfully used to produce PVDF membranes. What makes it particularly appealing is that it combines environmental benefit with economic feasibility, which makes it realistic even for larger scale production. The second case is another not toxic solvent, called the Tamisolve. It is very good to dissolving PVDF thanks to its chemical characteristics, which are similar of the main traditional solvent used for the membrane preparation, but this is harmful. And this allows us to prepare high quality membranes solution without compromising performance or safety. The membranes are prepared in hollow fiber configuration. Here I show you the setup utilized for the fibers preparation, in both in the case of Polar Clean and Tamisolve. For Polar Clean, we tried to different conditions, and the best one is with the PVDF at 18% in weight. In the table, I reported the composition of these fibers, while the solution containing Polar Clean and PVDF pass through the spinneret, and by changing the bore fluid composition and bore fluid flow rate, we can modify the structure and the morphology of the membranes. Here I show you the main characteristic of the fibers prepared with Polar Clean as clean solvent. In particular, with the scanning electron microscopy, we can observe the structure and the morphology of the fiber. The fibers show a structure sponge-like with some void inside the fibers. In the table, I reported the main characteristics, and the fibers is appear with a good mechanical property, hydrophobic property, and a porosity enough for membrane distillation application. So after the characterization, the fibers are tested with in MD for desalting saline waters, synthetic saline waters. Here I report only the fibers with the best performance. The fiber give us a flux table in time. With the salt rejection ranging from 99.8 99.6%. For what concern the fibers prepared with the Tamisolve as solvent, the preparation is the same described before. Here the best composition is with the PVDF at 16% in weight. In the table, I reported the operating condition to prepare the fiber. As described before, here I reported the main characteristic of the fiber. The same analysis show the structure and the morphology. As described before for the fiber prepared with Polar Clean, the fiber prepared with the Tamisolve have a sponge-like structure, but with a macro void in the internal part of the fiber. Here we have an higher hydrophobicity property with a contact angle above 90 degree always, and good porosity and good mechanical stability. The fiber are also tested in membrane distillation with the operating condition reported in the table on the right of the slide. The membrane with a synthetic salt solution show a stable flux and a salt reaction of 99.99%. So this membrane was also tested with organic compound dispersed in the solution containing the salt. Was tested for 30 hours in continuous without show wetting or a reduction of salt rejection. In conclusion, the membrane technology represents a mature and efficient and sustainable solution to prepare for the process intensification strategies. The introduction of eco-friendly solvent can help us to prepare membrane without decrease their performance. The case of studies with using polar clean time solve demonstrate as how these solvents can be used to prepare membrane, and the development of more environmental friendly materials and process support the transition to a circular economy, promoting a more responsible use of natural resources. Thanks for your attention.
Thank you very much, Mirko. So now we can open to the last session, the Q&A session. So you are free to ask whatever you want. I don't see any
even in the
raising
chat,
hands.
if you want. Yeah.
Or any message in the chat, but if you want to ask, feel free. And in the meantime, I would like to ask you to take a minute. I don't know if you can see my screen. I would like to ask you to take a minute to share your feedback, just framing with your mobile camera the QR code that's linked to a very short survey with just few questions regarding the webinar. So if there are no questions, we can conclude. So you will receive a video recording of the event via email in the next few days. And thank you for participating in the first public Melodizer webinar. And thank you to all the speakers.
Thank you.
Thank you.
Thank you. Bye.
Bye.
Bye bye.
Bye. Bye.